Have you ever stopped to think about how you can be on a video call with someone like halfway across the world, and there's almost no lag? It feels like magic, right? Well, it's not quite magic, but it's incredibly close. It's all thanks to this massive, invisible network that connects, well, everything. Today, we're going to pull back that curtain. We're going to see exactly how it all works. Let's dive in and demystify the world of telecommunications.
You know, if you look at an old rotary phone and then look at the Wi-Fi signal on your laptop, they're basically doing the same thing. They're just different tools for sending information over a distance. But the real question is, how? How does your voice or a text message or an entire movie actually make that journey from point A to point B? That is the big mystery we're going to solve together.
And believe it or not, the clue is right there in the word. Tele, that's just Greek for at a distance. And communication, well, that's just sharing stuff, right? So telecommunication is literally just communicating from far away using electronics. It's this amazing puzzle that we've been getting better and better at solving for more than 150 years. And what's really wild is that everything, from a simple phone call all the way up to the entire internet, is built on this exact same blueprint, this simple diagram. You've got a message, a transmitter to send it, a channel for it to travel on, a receiver to catch it, and then its final destination. So let's do it. Let's build this thing one piece at a time.
All right, first up, the message. Before we can even think about sending anything, the message itself has to exist. And it can only exist in one of two ways, analog or digital. And this, right here, is the Great Divide. This is the choice that basically defined all of 20th century technology.
So what's the deal with these two? Okay, think of it like this. An analog signal is like a smooth ramp. It's continuous, it flows, and there are infinite points along the way. Just like the sound waves your voice makes. But a digital signal? That's more like a staircase. It's made of very specific separate steps. Think ones and zeros. It's perfect for things that are already in pieces, like the letters in a text message.
And you can really see the difference here. Over on the left, you've got that smooth, flowing analog wave. It's basically a direct copy of a sound from the real world. Then on the right, you've got this clean, blocky, super precise digital signal. Two completely different approaches to grabbing the exact same piece of information.
So that brings up a really good question, right? If the analog signal is a more truthful copy of the real world, why did digital take over? Pretty much everything we use, our phones, TVs, music, it's all digital. So why did the staircase beat the ramp?
Well, the answer comes down to one big bad enemy: noise. See, as any signal travels, it picks up static and interference. It gets distorted. For that analog wave, any bit of noise is permanent. It gets a little fuzzier, a little worse with every copy. But for digital, because it's just ones and zeros, a device called a repeater can look at a messy signal and say, oh, that's definitely a 1, or yep, that's a 0. And it can then create a perfect, clean copy over and over and over again. Flawless every time.
So here's the bottom line. Being immune to noise gives digital these huge game-changing advantages. Your signal quality is always consistent. You can copy a song or a movie a million times, and the last copy is just as perfect as the first. Oh, and it's way, way easier to encrypt and keep secure. And that, my friends, is why digital won the war.
Okay, great. So we've got our perfect digital message. Now what? How does it actually get anywhere? Well, let's move on to the next piece of our puzzle, the channel. Think of this as the actual highway our information is going to travel on.
And we've got a few different kinds of highways to choose from. We've got the physical ones, wires like the copper and coaxial cables buried under our streets. Then there's the wireless route, sending signals right through the air with radio waves. Or we can go big and beam them up to space and bounce them off a satellite.
And this shows you two totally different ways we've figured out how to beat distance. On the left, you've got your classic ground-based or terrestrial communication, connecting buildings with physical cables or even beams of light. And on the right, that's satellite communication. We shoot a signal up, that's the uplink, and it gets beamed back down, the downlink, letting us cover absolutely massive areas of the planet.
So we have our information highways, but how do we get our message onto them? It's not as simple as it sounds. Our little ones and zeros can't just hop on for a ride, especially not on those wireless superhighways. They need a special ticket to get on. And that's where the transmitter part of our blueprint comes in, with a really clever trick called modulation.
What on earth is modulation? Okay, the best way to think about it is like mailing a letter. Your message, your voice, your text, that's the letter itself. It has all the information.
But you can't just toss it out the window and hope it gets there, right? You have to put it in an envelope and give it to a mail truck. Well, modulation is exactly that. It's the process of putting your low-energy message onto a big, high-energy carrier wave. That's our mail truck, which is built for long-distance travel.
Let's actually see how this works. So this wave here, the one labeled B, this is our message. This is the information. Think of it as the actual sound of your voice. It's a pretty low-energy wave, and by itself, it really can't go very far at all.
To make the long journey, it needs a ride. And that's where this comes in. The carrier wave, labeled A. This is a simple, powerful, high-frequency signal. It's got the muscle to travel across town or even across continents. But right now it's empty. It doesn't have any information in it. It's just a blank mail truck waiting for a package.
And now for the magic trick. Modulation basically imprints the shape of our message right on to that powerful carrier wave. Just look at the result at the bottom, wave C. See how the height, the amplitude of the big wave now perfectly mimics the shape of our original little message? The information is now encoded, packed up, and ready for its journey.
Okay, so why do we do all this? What's the point? Well, the payoff is massive. Here it is. Higher frequency signals can be sent and received by much, much smaller antennas. This one single trick is the reason you can have a powerful radio transmitter and receiver inside your tiny smartphone, instead of needing to carry a giant antenna on your back. It's a total game changer.
All right, so we've cracked how to send one message from one place to another. That's great. But our world isn't just about one conversation. We need to connect billions of people, billions of devices. So let's get to the final and maybe most important piece of this puzzle. How do we scale this whole thing up?
So the simplest network you can possibly imagine is this. Just two phones connected by a single wire. A point-to-point connection. It's perfect if you only ever want to talk to one other person. But for connecting a whole town, no way. It's totally impractical.
I mean, you can see the problem right away. To connect an entire town this way, would you have to run a dedicated wire from your house to literally every other house? Can you imagine that mess? It would be a complete nightmare of cables. There just had to be a better way.
And there was. The solution was to create a central hub, the telephone exchange. Now, instead of connecting to everyone, you just needed one wire connecting you to the exchange. And when you wanted to call someone, a real person, an operator, would take your plug and physically connect it to the jack of the person you wanted to talk to. Just like that, the circuit was complete. This was the first network that could actually grow.
Fast forward to today, and we've taken that central hub idea and scaled it up to the entire planet. That's what the internet is. It's a network of networks. And instead of a human operator plugging in wires, we have these incredibly smart devices called routers. They act like super fast, automated mail sorters, instantly finding the best possible path for your data to travel across this massive global web to connect you with any other device, anywhere. And there you have it. We started with that super simple blueprint: message, transmitter, channel, receiver, and we built the whole system piece by piece. We saw the big showdown between analog and digital, we learned the clever trick of modulation, and we saw how networks grew from a single wire to a global web. We've built this incredible, invisible infrastructure that has totally changed what it means to be human, which really only leaves one question. What's the next block we're going to add to this diagram?